Hello everyone. In this video we are going to talk about following a trajectory with the robot end effector. Let's say, for example, you want to have your end effector, which is a pneumatic gripper, grab a pen and then draw a shape, right? How would you apply the control so that you can achieve such task? So there are two ways you can do it. One is because your goal is motion control, really. So one way to do it is you directly perform the control in the task space. The other way is no, you still do it in the joint space, but since the desired trajectory is given in the task space, you need to use inverse kinematics, right? So if I give you, let's say, x desired and y desired, and let's say I'm using this 2 degree of freedom planar arm. So this is the problem we are going to solve here. This is my robot here. And my goal is I want it to draw a circle for me, the end effector of the robot. So how do I achieve such a goal? So as I said, let's say here, this is what I have. This is the end effector. It's a gripper, and this is the top view of it. So there is a pen here at, let's say, this red spot. This is the top view of that red pen, and I really want it to basically draw the circle like this for me, for example, something like that. So if I call an arbitrary point on the circle, if I call it xd and yd, the desired x and y, so I can find the equations for xd and yd based on time, right? It's not hard. So if I know the location of the center, let's say the center is x0 and y0. Let's say the radius of the circle is r. Then I can say that x of d is equal to x0 plus r times cosine of t, and y desired is y0 plus r times sine of t. So I can get the parametric equations for x desired and y desired, and again I want this end effector point here to basically track that shape and draw the circle for me. So one way, as I said, is I say, well, I pass these two to my inverse kinematics calculator. So I sample that circle at a bunch of points, right? So let's say here this t at least has to go from what, 0 to 2 pi, correct, to draw one round over that circle. So between 0 to 2 pi, I sample my time at, let's say, a bunch of points, let's say 100 points, 1,000 points, something like that. And then that gives me 100 or 1,000 x and y desired values. I apply inverse kinematics to each and every one of them, correct? And that gives me a bunch of what? A bunch of theta 1 and theta 2, or in this case q1 and q2 of t. Again, it is proper to say ti because we are really trying to sample. So if you remember from our previous lectures on inverse kinematics of this robot, what do we have? Q2, if you remember, was what? Was arc tangent to d of plus or minus square root 1 minus d squared, and d, where d was a ratio, and that was x of the end effector, correct? And then y of the end effector, so in this case x desired end effector plus y desired end effector, and then they are all minus sign. A1 and A2 are positive signs, so it is going to be a1 squared plus a2 squared minus x desired at ti, the whole thing squared, minus y desired at ti, the whole thing squared, divided by 2a1, a2. And there are two solutions, elbow up and elbow down. So let's say here we stick to the positive solution. And then q1 was arctangent 2 of y and x minus arctangent 2 of a1 plus a2 cosine of q2. And then this was the cosine component. The sine component is the first one, because remember it's y and x or sine and cosine. So it is going to be a2 sine of something, right? So this is ti. So we apply inverse kinematics, we get Q1 and Q2, and now this Q1 and Q2 are really now going to be what? They are going to be Q1 desired and Q2 desired. If your joints follow these two angles, then I'm sure that the end effector is going to be X desired and Y desired, which is exactly on the circle. And now that I have the desired angles, guess what? I exactly use the linear feedback linearization method that we saw in one of our previous methods. I pass this Q1 and Q2 desired to it, and the outer loop will cancel the nonlinearities. Then the inner loop will make sure that the error does converge to 0, the error in angle Q, correct? So that is exactly what you see I have done here in this bottom portion of my Simulink. So here I have this X desired and Y desired in this subsystem. My X desired is 0.018 plus 0.05 cosine t. So, and then YD is 0.1 plus 0.05 sine t. So radius here is 0.05 for the circle, and the center of it is at 0.18 and 0.1, and both of these are sine functions. All I needed was I changed the bias, the magnitude, and the phase. So here the amplitude is 0.5, the bias is 0.01, and the frequency is 1, and the phase is 0, right? And for the other one, in order to make sine into cosine, I added a pi over to phase to convert it to cosine. So you see I have bias, I have amplitude, phase, and frequency, okay? So that's X and Y. That makes sure that I draw a circle, center that, as I said, 0.18 and 0.1 with radius of 0.05. And I chose these values such that this D, parameter D that I mentioned here, does have a solution. Because if this D is anywhere outside the range -1 to 1, there will be no solution. So remember, this number has to be between -1 to 1 for this robot. Okay, so now if we go and look here, you see these X and Y are passed to the inverse kinematics. And inverse kinematics is exactly implementing those equations I just told you, and pass out the Q1 and Q2 desired, which are these two, and now I pass them exactly to the centralized multivariate control in the joint space that we have seen in one of our previous videos. So I pass them as the desired Q1 and Q2 to this outer loop block where the derivative of them is used as the feed-forward term, and then the subtraction of Q desired minus Q is error. You apply a PD control here and add all of this together. And then you also have this term, which does feedback linearization and cancels all the nonlinear terms. And this one here, and then passes the result to the robot. So this is your inner loop, right, which receives AQ from the outer loop, creates the torques, pass them to the robot, and then will generate what? The actual Qs. And here, on the other side of the block, I use forward kinematics, which takes Q1 and Q2 and generate X and Y of the end effector. I have that one will generate for you the X actual and Y actual of the end effector. So now you can compare the actual X and Y of the end effector versus what? Versus the desired X and Y of the end effector, which are those sine and cosine components, the one that basically create the circle. Okay, and I will display those versus each other in the XY plane, so you see that the robot is doing its job. The other approach that you can have is you do the control in the task space directly without using this inverse kinematics block. How would you do that? That's, again, we have seen that part in our previous video, and the solution was we bring our equation into the task space, the equation of motion. And here, if we consider this capital X to be pose of the robot, then the first time derivative of that is the end effector twist, which is JQ dot, and the second derivative of that is the end effector acceleration, which is JQ double dot plus J dot Q dot. Here, if you remember, we kept the inner loop the same. The outer loop, the AQ term, was a little bit more involved, right? So it was not as simple as this. It was still the feed-forward plus PD control, but here it was a little bit more involved. So you still see this is the PD control, and this is the feed-forward term. And here, because of this extra addition that you have in the acceleration of the end effector, you have to subtract the term J dot Q dot, and then you have to multiply the whole thing by J inverse. So definitely the AQ term does have more involvement in it. It does have more calculations for the outer loop, but the good thing is you can do everything based on the error in the task space, not the error in the Q space. And this alternative algorithm is exactly what you see here I have done on the top. So what I do here is, if I want to make the pose of the end effector, I use my forward kinematics block. So when Q1 and Q2 come out, this forward kinematics block give me this pose. This pose is the same as this capital X that you can see here. So I have the pose. I also have the twist. So twist, as you know, it is what? It is J times Q dot, and that's exactly what you see here, right? This is the result of J times Q dot all multiplied together. That gives you X dot and Y dot of the end effector in this case. The forward kinematics is the same. The inner loop is again similar. The outer loop this time is different. For the outer loop, I need to do a bunch of calculations, as I told you. Not only I need the P and D term, I need to calculate J dot term, I need to calculate X double dot term or get it from somewhere. I need the J inverse and a bunch of other things, right? So if you go and look here, this is the inverse of Jacobian, that is the XD double dot KP times X error plus KD times X error dot minus J dot Q dot. Okay, so you have a bunch of things, and here I use my omega equal 4. So KP, which is diagonal of omega squared, is going to be 16,0016, and KD, which is diagonal of 2 omegas, is going to be 800 omega 008. Okay, so this outer loop is now there, and I have also calculated my xd dot and xd double dot by literally, since I know these guys, I can calculate their derivatives directly here because they are predetermined. So I can directly pass it to them instead of me using what? The derivative block like I did here, and numerically take the derivative, because numerical derivation is always not as accurate as exactly analytic derivation. So here, let's say when my x was 0.18 plus 0.05 cosine t, what's the derivative? It's going to be negative 0.05 sine t, correct? So I could exactly make sure this signal here is exactly negative 0.05 sine t. So you see amplitude 0.5, frequency 1, and by adding a pi to sine, I make it negative sine. Okay, so that's exactly, or this cosine term also, right? That's the derivative of negative cosine. So it's going to be basically a positive cosine. It's going to be well, the derivative of sine, I'm sorry, the derivative of sine is going to be cosine. Cosine with respect to sine has a pi over 2 phase advance, which you see I have added here. So I have added my dot and the double dot terms, again analytically here, just to take advantage of the fact that I know my x desired and y desired ahead of time, and I can do all of those analytically. And I know them as a function really in this case. And everything else is the same. They are very similar approaches. And you might say, well, if I can do everything in the joint space as I learned, why should I do everything in the task space? Because they both perform the same goal. They want to make sure the end effector draws a circle. So why the top one looks a little bit more complicated than the bottom one? And it is, as long as this outer loop control, which is this rule here, looks a lot more intimidating than this one. And it has a little bit more calculation. What does it need? It needs Jacobian and Jacobian dots. That's all it needs, or Jacobian inverse. So it does involve some calculations in it that the joint space control doesn't. What the joint space control does have, which makes it a lot harder, especially when your robot is complicated, is this guy here, inverse kinematics. Inverse kinematics calculations can sometimes be very costly, okay, very hard to achieve. For the sake of 2 degree of freedom robot, the equations are extremely simple. And so the computation of that is probably much less than J inverse and J or J dot, or the same level. As the robot gets more and more complicated, keep in mind that calculating forward kinematics and Jacobian many times might not be as hard as inverse. Okay? I mean, as long as your inverse calculations is always possible analytically, it might not be the hardest thing in the world. But for many robots, the analytic solution does not even always exist. You know, you can guarantee inverse kinematic solution when your robot is not redundant and when it has a spherical wrist, if it's 6 degrees of freedom or so. So not always that's the case, that you have such analytic formulas like this possible, and that makes your bottom method a little bit harder to work with than the top one, which directly works in the task space, and it never needs you to calculate what? Inverse kinematics. Okay, because calculating, as I said, forward and Jacobian and so on, as long as you are using DH method, is kind of not so difficult. Okay, it's a very systematic approach. You follow the DH convention, you can always achieve forward kinematics, you can always get Jacobian. But inverse, there is no guarantee on that. So in this case, there is solution for both of them. So here I have simulated in this Simulink file both of them, and I plot both of them versus the desired value, and I'll also show you an animation of the system So this is my script that runs the Simulink and does the plot and animation. So let's go ahead and run it. So here, my end effector was here in the beginning, and you see it converged toward the circle, and now it is what? It is easily, the end effector, which is the red spot, is following the circle, right? So you see, the robot is exactly doing its job, and this is the plot of what? The black circles are the desired trajectory, okay? The red squares are the inverse kinematics in the joint space, the one that I used inverse kinematics for, right? The bottom system. And the blue triangles are the one on the top, the one that I did everything directly in the task space. As you can see, they are all converging. They are all falling onto the same thing, okay? They are all working. Now, let me do one more thing, and let me just add some line here, so at least I keep my desired trajectory together, and I show you animation one more time. There we go. So as you clearly can see, although my start point was not on the circle, very fast, the robot converged toward the circle, the end effector, and now you clearly see what? It is doing its job. Okay, and you can simulate it for a lot more time, and you see that it keeps going on the circle forever. And if you look again here, you see that my algorithm does do its job, whether the top one or the bottom one. The difference might be a little bit if you zoom into this beginning area here, where I'm getting what? Closer to the circle right in the first cycle of it here. Maybe it is a little bit more revealing in here. So as you can see, the two algorithms, the top one and the bottom one, kind of come hand in hand, right? There is no difference between them. They are both showing kind of the same level of accuracy, correct? You don't see much of a significant difference between them, right? So again, in this case, there is not a really big mathematical advantage over which one you want to choose. But you clearly see the errors are getting smaller and smaller, and finally my points what? Fall onto the circle. And you might say, why do you have 2 points next to each other? Well, one of them is for one cycle, the other one is for the next cycle that the robot tries to follow. Okay, but as you can see, almost all of the points are for the top and the bottom algorithms. They are on the top of each other. So really, I do not see much of a difference. As you can see, they are almost identical. Okay, so again, for this simple example, none of them will provide a big advantage. But remember that the inverse kinematics is not always available, and it's not easy to calculate. So in many cases, it's better to directly do everything in the task space instead of first inverse kinematic, then doing it in the joint space. Okay, so hopefully this simple video and animation was useful to you. I will provide the download links for this M file and for the Simulink file for you. So hopefully you can use it and learn a little bit better about motion control in the queue space and the task space. And I will see you in my next video. Thank you.